All right, let's get started. Oh, my voice. All right, so quick reminder, I'll have Discord lecture channel open on my phone. If you got questions, hit me up there, or the old-fashioned raise your hand works just fine too. So let's do it. Anybody have questions before we get into it, before we talk about Java data structures? All right, let's do this. So Java data structures, array list and hash map. Got a lot of stuff. This is still a pretty healthy clip we'll be going at today. And then Friday, I did say next Monday, if anybody pays attention to me, I don't know. But by Friday, we actually will slow down. I know you pay attention to me when I'm doing content, but I don't know. Whatever. But on Friday, things will slow down. Friday is just Java examples is all it says on the course website. And it's not going to be any new content unless we don't get through today's slides. You know, I might clean up some slides at the beginning. But it's going to be just reviewing what we did. I plan on going into IntelliJ, coding things, showing you how IntelliJ works. Probably talking about the homework, how to start the homework and all that good stuff. What Autolab feedback means. Really whatever will help you understand the Java content. But anyway, let's get into it. Most of you should have seen this in 115, so I only have like 3 slides on this. But just talking about memory, because we talk about memory a lot in this course and in 115. We're constantly using memory diagrams, using the tracing tool, and going through things with memory. Actually, maybe that's what I'll do Fridays, pull up the tracing tool and start using that in lecture. Instead of doing memory diagrams and slides, I got to start doing them in the tracing tool. So let's talk about what we actually mean by memory. And what I mean is this thing, these RAM sticks that we have in all of our machines. This is what I mean by memory. It's always random access memory. If your device has, X gigs of RAM, that's what we're talking about, or I guess we just call it memory these days. But that's what I mean when I say memory is whatever's stored on these things, which is our temporary storage for our executing programs in the computer, as opposed to hard drive, which is, I got rid of that slide too, as opposed to hard drive, which is our long-term storage. So if we need something to live longer than the execution of our program, we'll save it to a file that gets saved to disk, and then we can load up that file in any other program, any other process that we run, any other program we run. But as our program is running, everything for that program, unless it's doing file I/O, everything is going to be stored in memory. So when our program starts, we're going to go to our operating system, and I'll usually say operating system. We're in Java, so our program is going to talk to the JVM, but as I'm blanking on the word. But then the JVM is going to go talk to the operating system and manage memory that way. But in generic terms, for any programming language, at some point, our program has to be communicating with the operating system, whether there's a liaison, that's the word I'm looking for, whether there's a liaison or not, doing the negotiation for us. We need to get memory, and memory is managed by the operating system. When you get to 220, you're going to see this much more directly in your code. You'll write lines of code that says, ask the operating system for this much memory, called malloc or memory allocation. We don't have to get that into the weeds in 116 using Java, but this process still does happen at some level. So when we start our program, we're going to get a chunk of memory. We get a chunk of this RAM stick that's just for us, just our purposes. We get to use that memory for all of the storage of our program, and we have to stay confined in that chunk of memory. We can't go outside those bounds. The operating system says, here's some K of memory, you get this amount of memory, and anything before that might be used by another program, anything after that might be used by another program, and even if it isn't, the operating system won't let us go outside these bounds. It's just simply not allowed. We don't have access to it. We don't have permission from the operating system to access any memory outside of our specific chunk to be able to do everything we need to do with our program. And this is called stack memory. So we start our program, we get stack memory. Of course, the left side of our memory diagrams, that's all stack space. That's what we get allocated to us when we start our program. If we run out of stack space, we use up all of that space, and we try to use one additional byte of memory the operating system, the JVM, they both get really mad at us and say, your program is done, you're cut off, crashes our program, and gives us a Stack Overflow error, the namesake of our favorite site. Stack Overflow error means we overflowed the stack. We ran out of memory, tried to use more than we were allocated, things break. This is a last in, first out data structure that is literally a stack. The stack memory is a stack of stack frames and variables. Well, actually just stack frames in Java. It's a stack of stack frames, and each stack frame contains variables. And we can only access the top stack frame on the stack. Visually, the top of the stack is on the bottom of our memory diagrams, but conceptually, it's the top of the stack. Whatever stack frame is on top of the stack, that's the active stack frame. The variables in that stack frame are the only ones we're allowed to access. We can't access anything else on the stack, any other stack frames. We can only add stack frames to the top of the stack on top of that top stack frame, and we can only remove the active stack frame that's on the top of the stack. So it does follow this last in, first out data structure. The bottom of the stack, the first stack frame is always our main method stack frame, and once that stack frame's off the stack, our program's over, but we can only add stack frames to the top of it and remove from the top. In stack, that's what we use mostly in 115. Use the heap a little bit. For what we're going to use the heap for today, it's going to be the same as what we use the heap for in 115. And then when we start introducing classes in 2 weeks, we're going to use this for a lot more. We're going to see a lot more heap in action. But when we start our program, we get memory allocated to us. That's our stack space, and that's it. It's one fixed continuous chunk of memory, and that's it. That's whatever we get, that's what we get for the entire execution of our program for stack space. If we do need more memory, because sometimes we're just going to need more memory, we're going to have large amounts of data that we need to store, that's what we're going to use our heap space for, or heap memory. So with the heap, this is more dynamic memory that we can ask for as our program's executing. So we say, hey, thanks for that stack space and all, but I really need more space. We go to the operating system and say, I demand this much space, or however much space we need. It might be gigabytes of memory. We're going to say, I want this much memory. The operating system, either it's going to say, no, that's too much, get out of here, or usually the JVM actually limits us. But it's going to say, that's too much, get out of here. Or in most cases, normal operation, it's going to say, okay, cool, let me sort that out. Find a space somewhere in memory, somewhere that's not going to be in our stack space, some other chunk of memory. It's going to allocate that memory to us, give us that memory and say, okay, this chunk of memory, you are allowed to use this space in addition to your stack space. And we can keep going back to the operating system saying, hey, I need more space, I need more space, I need more space. And whenever it gives us more space, that's going in the heap. So this gives us a lot more flexibility in what we can do. There's no last in, first out data structure. There's no one continuous block of fixed memory that can't expand. We don't have those restrictions. So restrictions are fine for what we use the stack for, but when we need more flexibility, we need to head over to the heap. And the first time that we need to do this is whenever we have a data structure. If we have a data structure and we slap that thing on the stack and we fill that up with a whole lot of elements, we're going to run out of stack space pretty quick. Stack space isn't huge. It's not tiny either, but it's small when we're talking about data structures. If we want to have a data structure with 1 million elements in it, it's not going on the stack. It's not going to fit. So for a lot of reasons, the getting rid of the last in, first in, last out restriction, getting rid of the continuous block of memory, being able to order up large chunks of memory, it's just more flexible, more dynamic, and lets us do a lot more than what the stack affords us to do. So that's why we use heap space. I say heap memory. I always call it heap space, but heap memory, it's the right side of our memory diagrams. Okay, any questions on that? That's all I want to talk about memory. I assume they talked about that in one way or another in 115 anyway. So I don't want to dwell on it too long. Also, 220 will go in much more depth on these things. To get to the next stack frame, do we need to cross out the one before it? Yes. So when we cross out a stack frame, that means that stack frame was popped off of the stack. It's literally removed from memory and deleted. It is non-existent after that. We just cross them out so we preserve the history of the execution of the program. So we have that final memory diagram is a roadmap of everything that happened throughout the execution of the program. or else your final memory diagrams that you'd submit would always be just completely blank. After the program ends, all memory is freed up. That wouldn't really help us grade things. So we do need a full trace of all of the execution of the program. That's why we just cross things out. But in reality, those crossed out stack frames are removed from memory. They're actually just gone, deleted. They cannot be accessed anymore. So once a stack frame is crossed out, the one before it is now the active stack frame again. So if our main stack frame is added to the stack, we call a method, and then that method ends and we cross it out. The main stack frame is now the top of the stack again, and that's the active stack frame once again. So in our memory diagrams, the lowest stack frame visually that's not crossed out is always, always, always the active stack frame. And the heap uses references. That's the one thing I forgot to say on this slide. Okay. And I don't know, is it worth saying? The locations can change. It's not really important for our purposes in 116, but I'll mention it here. The locations can change. The JVM obfuscates all the actual details of what happens with memory allocation. And the JVM, to optimize things, might move things around in memory. We don't care where anything is in memory. We don't care if it moves. We don't care. As long as we have a reference to where the current location of that value is, of that data structure. Bless you, in our cases right now. All right. So with all that, I'm done talking about details of memory. Let's get into array lists and a memory diagram with an array list. So here's an array list example. With array list and hash map, I don't have a ton to say about them, but we do have to cover the syntax, so I got a few slides on each. Our array list, this is your list in Python. All of that knowledge, everything, all of your understanding of a Python list, transfer it right over to array list. It's mostly, we'll talk about some little differences, but it's mostly going to be the same thing. This is our sequential data structure. We have indices starting at 0 to the size of the array list minus 1. Same thing as a Python list, but some of the syntax is going to be different, and the syntax is what we got to talk about here. But the end product that we get to work with is mostly the same as a Python list. So think list in Python or array in JavaScript, but y'all didn't see JavaScript. I got to erase that bullet point, I guess. Vector in C++. It's been a while since I did C++. Vector, I believe, is the common one that y'all use. What other data structure? What other languages would you have seen? It probably covers most of it. Or array list in Java. All right, so this is our sequential data structure in Java that we'll use. There are others, but this is like the default go-to that everybody likes to use as their first sequential data structure. We will talk about linked lists. It's another sequential data structure, but that's got a whole week of content to cover that. We'll talk about that one as well. This is built into Java, but this we do need to use our first import statement. Arrays versus array list, question mark. Arrays we're not going to use in this course. The difference is, I got to think of my brief way of saying this. We'll encounter arrays very briefly in this semester, but when we do encounter them, I'm just going to show you real quick how to convert them into array lists, and then say, if you want to mess with arrays, go for it, knock yourself out. If you don't want to think about the difference between arrays and array lists, just convert your arrays to array lists and use those. Arrays are fixed size is the critical difference. Arrays cannot change size ever, which means if you create an array, you can't just add an element to it. Not allowed, can't do it, not possible. Can't do it. The same is kind of true for array lists. Array list is what we call a wrapper class for an array. It actually has an array underneath the hood that it uses, but it gives you the illusion that that array can change size by whenever you run out of room in your array, it'll create a new array of double the size, and then you can use that space until you need to increase the size, get a new array again. So it gives you the illusion of a dynamic size array and hides all the details from you, so you just pretend that it works the same way as an array, a Python list, or anything where you can... No, I can't go that far. But but it gives the illusion of an array that can change size, which is convenient. That's why we like to use it. Then we can talk about other things and hide the details of our data structures, and then save that for CSE 250. We got a lot more courses where you'll talk about the details of all these things. In 116, we do quite a few things where we kind of sweep the details under the rug and say, look, this course is about testing, OOP, and a couple of data structures. Let's focus on those things and hide some of the details. And that's one of the details that we like to hide. But if you want to mess around with vanilla arrays, go for it. Just know that you can't add elements to them. Import. So importing, this is where we want to use code from another class inside of our class. This, we're going to see this throughout the semester. You're going to be importing your own code too once you have projects that span multiple files, which is right from task 1. We call them tasks in this class. Right from task 1. If I say homework 1 or homework 2, I mean tasks. There's no two separate things. I do get that question from time to time. I'll mix like programming assignment, homework, task, project. All these words I use synonymously, and in each course I just use one of those words. Task is the one we use in this course. But task 1, I'm going on a tangent, but the reason we use tasks is because all 8 programming tasks for the learning objectives are all part of the same project. So it's one project with 8 separate tasks. So it made more sense to call them tasks. And you'll keep building and adding features to the same project throughout the whole semester. So task 1, you'll have your testing code in a separate class than the code that you're testing. So you have to import your code. So imports is something we'll have to think about from early on, starting with this slide right here. Import java.util.ArrayList. When you import, you have to use the fully qualified name for a class. What that means is package.classname. So the ArrayList class is in a file named ArrayList.java, which is in a package called java.util. So in the ArrayList class, in that file, the first line is going to be package java.util. So we specify the package name and then the class name whenever we're importing something. Now, we did use some classes that didn't need to be imported, like string and system. There are some classes that are just imported by default. Java says, hey, look, everybody uses these things. Like, we're not going to make you import string. So some of them are auto-imported. ArrayList is the first one that we're using, which isn't auto-imported for us. And all our primitive types, which is any type that starts with a lowercase letter, is also auto-available to us. We don't have to do anything extra to have those values, those types available to us. ArrayList we do, and the second one's going to be HashMap. We're going to have to import that as well. Once we import ArrayList, we're allowed to use the ArrayList class in our code. If this import isn't here, this line is going to have an error on it, and it's going to say, I don't know what an ArrayList is. And Java's going to get mad and not run our code. So we need that import statement for this line to compile, so we can start using the ArrayList. I said class, but I should say type. And we're going to see a little bit of syntax here that we're going to, in week 4, here's an example of what I was saying earlier. I did update these slides, but it looks like they didn't make it to the live site. I'm not going to mess around with it right now. But in week 4, we're going to start talking about classes, constructors, objects, all that stuff. For now, let's just say we need this keyword new when we want to create a data structure of type ArrayList. We're going to say new ArrayList, and this is where there's quite a bit more syntax than in Python. New ArrayList, in Python you just say R1 equals your brackets. New ArrayList, and then angle brackets and parentheses, semicolon. This is how we're going to create a brand new empty array list. The brackets, the angle brackets, are the type parameter list. We only need one type here. We're going to specify what type this array list is going to store. So this is one of the big functional changes from Python to Java. Java data structures can only store one type of object. So when I create this array list, I'm going to create an array list of integers, and it can only ever store integers. On the right-hand side of the equal sign, we can type integer here, but it is actually optional on the right-hand side. One of the few times where Java says, you know what, I got you, I know what you mean. Because we're assigning this array list to a variable of type array list of integer, it doesn't make us type integer twice. So one case where we get to cut down a little bit of typing. But you can, if you want, you can type integer right here as well. And then this is calling a special method called a constructor. Again, details to come in week 4. We'll dive into it deeply. But this is calling a method. Since it's calling a method, we do need an argument list to match the parameter list. And we're going to give it no arguments, but we still need this empty argument list because we are calling a method. So we have an empty argument list. We don't want to use any arguments. We're just creating an empty array list. But the type parameter list and the argument list still need to be there, even though both are empty in this case. They have to be there for things to compile, for things to work. On the right-hand side, where we are specifying the type parameter here, this is a variable of type array list of integer is the way we say this. We have a type parameter of integer, which means our array list here can only ever store integers, and it's going to be assigned an array list of type integers. So the only type that we can store in this data structure, this array list, is integer. So not just every variable needs a type, but every data structure needs a secondary type called a type parameter that it needs to specify which type that data structure can store. And if I try to ever put a double in this array list or a string in this array list or an array list in this array list, it's not going to work. Java's not going to run my code. It's going to say, you told me that's an array list of integers, and you tried to put something that's not an integer in there. Not going to work. Again, one of the only exceptions would be an array list of doubles, and I try to stuff an int in it. Java's going to help me out there and say, okay, you're good. We'll figure this one out for you. But most type mismatches aren't going to work for you. And your type parameters must be class types. So there's a difference in Java between a class type and a primitive type. We'll talk about this more throughout the whole semester, but I'll try to get the whole succinct form of this conversation out right now. Our class types always start with a capital letter, and our primitive types always start with a lowercase letter. Our primitive types are always stored and passed by value. So if I have a lowercase int int, and I assign that to another int or pass it to a method, it's always going to be passed by value. It's just strictly a value. But whenever I have a capital letter, like capital I integer here, it's going to be passed by reference, meaning this is a reference to an object on the heap. So everything with a capital letter is stored on the heap. Everything with a lowercase letter is stored directly by value in that variable, often right on the stack itself. But everything with a capital letter is by reference. We'll bend that rule a little bit. We already bent that rule with strings. You know, a string starts with a capital S. It is an object type. It is an object on the heap. But we do pretend that our strings are primitives. We pretend it's a lowercase s there, just in 116, just for our memory diagrams. Because they behave exactly like primitive values, we actually get away with that. They have a lot of complex behavior that ends up being, they behave like pass by value. Deeper conversation about that in week 4 when we have more object types. But for now, we can't create an array list of ints, not allowed. So we have to use this different type. We can't do array list of lowercase int. It will not work. We have to use class types, not primitive types, for our data structure type parameters. Luckily for us, Java gives us these class equivalents for each primitive. So capital I integer, capital D double, capital B Boolean. These are the class equivalents. And in most cases, Java converts between these without us having to do anything. So, something called auto boxing. If we need an integer and we give it Java an int, it'll be like, I know what you meant, and just convert that int to an integer for us, and vice versa. So Java's really good about this. There are some exceptions, and one exception will be when it's a return value for a method, specifically on the homework assignments. You don't quite get away with that. So as a rule of thumb, in this class, we're always going to use the primitive types unless we have to use the class types, class equivalents for the primitives. So that's data structure type parameters. End of list. That's the only time we're going to use the class equivalents of our primitives is when we have a type parameter in a data structure. There's no other case that'll come up in the semester where we can't use int, lowercase d double, lowercase b boolean. So whenever you're writing your code, make sure you're using the primitive types, especially when it's the return value of a method and the homework says this method returns an int or lowercase d double. Don't have it return integer or capital D double, because you submit to Autolab and it says your code's broken. And I get frustrated every time I have that question in office hours, because I always make a big deal of it in lecture. And the feedback in Autolab will say, check to make sure that you have lowercase d double. And somehow we still get that question in office hours. So don't be that person. Always use the primitives unless it's a type parameter. Why don't we call the new constructor on an integer? For an array, you would call the constructor on an integer to specify the size of the array. Array list, if we don't specify, we can specify the default, the initial size of the underlying array if we want to, if we know what that value is and we want to save a millisecond or two. But by default, if we don't give it any arguments, it's going to start with its built-in default initial size, and we're comfortable with that in almost every case. But we could give an integer there for a default size. Or initial size, not default size, initial size. All right, and since ArrayList is a class, it's hard to talk about that because we don't know classes and objects yet. But there's no array syntax with ArrayList. We cannot use this square bracket syntax with an index to access or modify any values in the array list. It does not exist. So in Python, we would use these square brackets, and that's how we would access our data structure values. Oops. That's how we would access our stuff. Not allowed in Java. That syntax doesn't exist in ArrayList. Because ArrayList is a class, it's a regular class, all classes have our methods. So every time we want to do anything to an array list, we have to call a method. And this will be true for most things in Java. Anything we want to do, it's going to be a method call. So if we want to add a value to an array list, .add, and then the value we want to add. And if we want to get a value, .get, and the value we want to get. Whereas in Python, we would say array1, actually we would do I always forget if it's push or append, but it's one of those two. One of them's JavaScript and one of them's Python. I always get them mixed up. And then this, we would do array in of x using this syntax. Not allowed in Java. That syntax does not exist. With ArrayList. It doesn't exist with ArrayList. It does, it's on the slide. It's right here. We can use it for args, which is a plain array. But it's not something we're using, not with ArrayList. It's not valid syntax. Okay, any questions on this so far before we do the memory diagram? Yep. We can. The syntax is a little more cumbersome. I think on Friday I could show an example of that. I think that's the first convenient time to show it. So I'll have IntelliJ open. I can show that open. I'll verbalize it right now, but it's hard to visualize. New array lists, your angle brackets, and then inside the constructor argument list, you would do arrays.asList, and then in parentheses a comma-separated list of values, and make sure you import arrays before you do that. Would be the way to do it. But I'll show it in code on Friday. If you remind me on Friday, I'll do it for sure, but I'll try to remember to do it regardless. Because that's helpful for the average method in task 1 as well, to be able to write your test cases without being bogged down with .add. So that's a really handy thing to do for task 1. So I want to show it. Friday's probably the best time. All right. got to add my pointer finger to my unlock thing. All right, so this is memory diagram. It starts off very similar, but to the ones we've done so far, it's going to get pretty different quickly. But if you've gone through 115 last semester, it's not going to be anything brand new. And my way of representing it's going to look a little different. When I start using the tracing tool, I'll do it the way that you're used to seeing it. But I'm going to show my arrays and hash maps a little bit different, but that's just for the slides. Don't worry about it. We're going to do things the same way in the tracing tool. But when we get to array lists, since array lists and hash maps are going to use the heap, we're going to put these things in heap space over on the heap in our memory diagrams. So when we create a new array list, whenever we see the keyword new, we know we're creating a new thing on the heap. The new keyword will go to the operating system, ask for memory, enough space to store this new object that we're creating, and then our constructor is going to go to that space in memory and populate whatever it needs to populate, do whatever it needs to do over there. So we have this new array list in memory that's being created in the heap. And we're going to create two columns for that, one for indices, one for values. In the tracing tool, it's name and value, and the names, you're just going to put the indices of that you want for the array list, or that you have for the array list. I'm going to say indices and values, but if you read that as names and values, this is the way it's going to be in the tracing tool. The type of your object would be array list, and then everything else is the same as anything else on the heap. I say that, but you've only seen lists and dictionaries on the heap. So, but it's going to work like your Python list did. Same syntax in the tracing tool. And we have references. Even after 115, refresher on references can be very helpful. So let's talk about references. Whenever we allocate memory in the heap, we get that space allocated to us. The operating system, go through that whole process instead. The operating system says, here's the amount of memory that you asked for. And what it actually gives us is the memory address for the first location in memory where that memory was allocated. Memory is specified by hex values. And we get the first hex value, where each hex value is like an index in a giant array. Our RAM, I forgot to say that in the earlier slides, but our RAM, our memory, is one giant array that's several gigabytes in size, tens of gigabytes these days usually in size. And we access the values by index. So when I say OX200 here, I have my memory stored at the hex value 200. The first byte of this array list is at hex 200 in memory, that index. If you don't want to think about hex values, that's fine. I'm never going to use any A through F in my slides. But this OX means the numbers hex value, not a decimal value. X all over the place just to say that this is the memory address. And Java actually obfuscates this. The JVM says you're not addresses. Oh no! Hope that wasn't falling off for too long. Hopefully my mic was by my leg. Hopefully it wasn't there for too long. I don't really need the mic for in the room, but the mic picks up for the recording for the video that'll be posted on Panopto. So some of the video might not have audio if the mic doesn't pick it up. All right, so the OX means this is a hex value, and this is the index where things are going to be stored. That's what I was saying. The JVM will obfuscate this. We don't actually have access to the actual memory addresses, and like I said, the JVM can move things around in memory without notifying us, without telling us about it at all. But we are going to put the hex values in our memory diagrams because the concept of references is going to care about the memory addresses at some point, and then in 220 specifically, it will be the memory addresses directly that you'll manipulate. So we want to get you used to seeing these hex values, even if for now you just say, oh yeah, they all start with OX, and don't think about it too much beyond that. I'm fine with that. But these are memory addresses in our memory diagrams. And then what's stored in the variable R1 is just the reference. Just the reference is stored. So the stack, we have a finite amount of space and a fairly small amount of space. We can't use much stack space. The whole reason we went to the heap was for a lot of reasons that I explained earlier, but one of those reasons was so we can store large amounts of data. We have these massive data structures. If we copy those data structures and smash them on the stack, that's going to defeat the purpose. What's stored on the stack is just a reference, just the memory address, just the instructions of where we can find that array list in memory. So the stack is in one place in memory, and this variable is going to store another location somewhere else on our RAM stick, possibly even on a different RAM stick entirely, but it's going to store the memory address of where I can find the first byte of this array list. And once I'm at the first byte, I can access every part of that array list. But I only have a reference to that array list stored in my variables. So R1, we say, and I'll still say throughout the semester, we say it's a variable of type array list of integer, but really it's a variable that stores a reference to an array list of integers. R1 doesn't store anything more than that reference, which you can think of as a map, a road map that says, here's where in memory you can find an array list, the array list that you refer to. Very, very important concept. Again, you should have seen a bit of this in 115, but it will be critically important throughout this entire semester too. So any foundational knowledge you have of references and the heap is going to serve you quite well all semester. Okay, and then whenever we access our array, we have this dot operator, and you'll hear me say this so many times you're going to get sick of it. We have array1, which stores a reference. It does not store an array list. What the dot operator says, what it speaks to me anyway, is I know array1 stores a reference to an array list, and I don't care about that reference. None of us care about references. I don't want to say, hey, array1, what's the memory address where that array list lives? I don't care. I never care. The JVM won't even tell us that actual value because we never care where in memory that thing is. We never care. What I care about is the actual array list that's being referred to. And the dot operator says, follow that roadmap and take me to that array list. Take me over to the heap and show me that actual array list that you're referring to because you're a reference and I don't care about references. Take me to the array list. Dot operator does all that. Says, this is a reference. Take me to the object to which you refer. So whenever we hit the dot operator, we're following the arrow over to the heap. And then after the dot operator, we're at this different object. Oh, I got to get used to this semester again. You know what? I'm not going to find it quick enough. I like to point with my mouse, but I have the mouse pointer way too small to see. So I got to increase the size of it. But and my laser pointer doesn't work on the screen. My tools I'm hampered here. But anyway, we're going to follow the reference to the actual object. So after the dot operator, everything after the dot operator is no longer doing anything with the reference. After the dot operator, we're actually at the object that was being referred to. So we're at that object, and then we're going to call the add method with 10 minus x, which is 10 in this case, and call add when we're at that array list in the heap. We're calling the add method on that array list and adding that value. So the dot operator said, your reference, that's cool and all, but take me to your object. We hit the loop. We already talked about loops. I don't want to hammer that home again. But we're going to loop. Cross out the loop. X doesn't exist after the loop. And we ended up adding 4 values into this array list. When we print out an array list, Java will print it out as comma-separated values with square brackets. It's not super important, but I want to mention it. Yeah, that's all I want to say about that. That's the syntax of printing out an array list that Java gives us. And then since array1 stores a reference, we have this kind of magical thing, this trippy thing when you first see it. You're all going to get very used to this and crush this on the quiz. The very first quiz will test your understanding of this. We'll talk about it a lot more before this. But array2, we're going to create a second array variable an array list of integer or a variable array2 that stores a reference to an array list of integer on the heap, and set it equal to R1. What this does, whenever we have an assignment operator, what the assignment operator does is takes whatever's on the right-hand side and assigns it to the left-hand side. Now, that's obvious when it's integers. Of course, that's what it does, right? But what's on the right-hand side here? The value of R1 is not an array list of integers. Looking at the code, we might want to think that. But looking at the memory diagram, we can see that's not the case. The value of R1 is whatever's in the value column for R1, OX200. It's just a reference. It's one single hex value that represents a memory address. That's what's stored in R1. So when we have the assignment operator, guess what gets stored in R2? OX200. We didn't even go over to the heap and talk to that array list at all. The array list isn't involved in this assignment at all. We're just taking whatever's next to R1 on the stack and assigning it to R2. That's just the reference. All we did was move the reference over. Yeah. Yes. And it's critically important to know. It's very important to know. So there's only one array list in the code. So the question, if I go to R2 and change the value at index 0, is R1 going to see that change? Yes, absolutely. R1 is going to see that change because they're both referring to the same exact array list. So any change made through either variable is going to affect the other and vice versa. So there's only one array list in this example. Array 1, array 2, we add values to array 2. They're added to array 1 as well. They're two variables that refer to the same object. And that's, if you understand that part, then you're doing great in terms of references. Dot operator is kind of like a pointer. So when I say in this, I use reference in talking about this, but if you're coming from C or C++, there are both references and pointers. What I talk about here is more pointers. This behaves just like C and C++ pointers instead of C and C++ references. And maybe someday I'll start calling them pointers just to avoid any confusion there. But these are just like pointers, if you're familiar with those. If you're not, you will be in 220. And Ethan and Carl, they'll yell about me and they'll scream and say, why does he call those references in 116? We have references, they're different, they're something different. And they're absolutely right. This is called assign by reference, which is technically, going to the point that I just said, it's technically assigned by value, and the value that's being assigned is a reference. But just because I don't feel like saying all those words every time, hate me if you want, but I'm just going to say assign by reference. We're assigning a reference to another variable. There is assigned by reference and assigned by value, with the value being a reference, are two different things, and that is at the crux of the difference between references and pointers in C and C++. So I'll let 220 sort that one out. They'll tell you exactly what the difference is between those two things. Assigned by reference would actually be R1 storing a reference to the memory location of R1. So there is a difference, and I'll let 220 sort that out. But I'm just going to call this assigned by reference because we're moving references around in our code. I already hit this point quite often. So when we print array 2, we're going to get the same exact thing printed as when we printed array 1. But there's only one array in this example, in this code. And then we'll call this sum. Whenever we call a method that takes an object as a parameter, in this case, our object is array list of integer. So we're going to take a reference to an array list of integer, which we usually just say takes an array list of integer, Rn. We have this hidden line, this hidden assignment, array list of integer Rn equals R1. R1's value is just OX200. So our N's value is just OX200. Now we have three variables on the stack that are all referring to the same array list. There's only one array list that was ever created for this code. We did not create a new array list and copy this array list and copy all its values, create another one in heap space. We never did that. We just have one array list and 3 copies of its reference stored in 3 different variables. So if, we don't do it in this example, but if inside this sum method, we will do it throughout this semester, we went to rn.add or modified this in any way, that modification is going to be seen even after this stack frame ends and goes back to the main stack frame. R1 and R2 are going to see those changes, and their array list has changed because they're referring to the same exact array list. In this case, we're just looping and summing up the values in Rn. Here we're using the dot operator to access the size method, call size on the array list. That's going to return 4. And we're using .get, rn.get, follow the reference, go to OX200 on the heap, and call the get method to get each value. Loop through these, sum up the values. When the loop ends, X is no longer in memory at all. We're going to update the values stored in out to sum up all these values. I don't think I have to go into too much detail on all those. That's all review, even from stuff we already covered in 116 in the few lectures we had. But if there are questions, I guess I'll take them in office hours at this point. Returns and then prints. And then we won't get to talk about hash maps today, so I'll clean those slides up on Friday, and then we'll do go into IntelliJ and do examples. The short answer of hash map is they're like dictionaries in Python. That's my short one-liner of what hash maps are. But they're going to be a bit more complex.